Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. What makes a planet is more than its orbit around a star or its round shape. It is the story written in its atoms, the record of its birth, and the slow alchemy of time, pressure, and heat that have rearranged its matter into continents, cores, rings, and skies. To understand what planets are made of is to trace that story from the fine dust of a protoplanetary disk to the layered interior of a mature world, to read the chemical fingerprints in a distant atmosphere, and to glimpse the surprising variety of planetary recipes that nature can cook up. This essay takes you on that journey, from the simplest ingredients to the strangest combinations astronomers have discovered. With attention to the physical laws that sort materials into shells and the observations and experiments that reveal their composition. Planets form in the swirling disks of gas and dust that surround young stars. Those disks inherit the chemical makeup of the molecular cloud that collapsed to make the star, enriched by generations of stellar forges that produced heavier elements. Inside such a disk, tiny grains of silicate, metal, and ice collide and stick, slowly growing from micron-sized particles into millimeter pebbles, then into kilometer-scale planetesimals. Gravity becomes the decisive actor once bodies reach sufficient mass. They accrete material more effectively, clearing their orbits and building protoplanets. During this epoch, the local environment of the disk, its temperature, pressure, and the current mix of solids and gases determines which materials can condense and be incorporated into growing planets. The disk acts as a chemical sieve. Close to the central star, only refractory materials like metal and silicate can exist in solid form. Farther out beyond a characteristic distance called the snow line, volatile compounds such as water, ammonia, and methane freeze and join the solid inventory. That simple distinction underpins the broad dichotomy of planetary composition seen in our own solar system and likely in many others. Inner worlds dominated by rock and metal, and outer giants rich in gases and ices. Rocky material is the backbone of terrestrial planets. It is a mixture of iron, magnesium, silicon, oxygen, and lighter elements arranged into minerals. The simplest view divides a rocky planet into a metallic core, a silicate mantle, and a crust of lighter, less dense rocks. The core concentrates heavy elements, such as iron and nickel, sometimes alloyed with sulfur or other light elements. And beneath the tremendous pressure, these metals can behave in exotic ways that determine the planet's magnetic properties. Surrounding the core, the mantle is mostly silicate minerals, compounds of silicon and oxygen combined with magnesium, iron, and calcium, whose crystal structures transform gradually with depth under rising pressure and temperature. Close to the surface, lower density minerals form a brittle crust that can be fractured, uplifted, and weathered. The relative proportions of core and mantle depend on the original chemistry of the building blocks and the details of a planet's early history. Collision events can strip away a portion of the mantle or cause mixing that alters the iron fraction. In our solar system, Mercury's unusually large iron core hints at dramatic early collisions or preferential removal of mantle material, while Earth's mantle and crust host a diversity of minerals and an active plate tectonic cycle that recirculates material between surface and interior. Ices are another major class of planetary ingredients, but the word ice in planetary science carries a broader meaning than frozen water alone. Under cold conditions, many volatile compounds become solids. Water, carbon dioxide, methane, ammonia, carbon monoxide, and nitrogen can all be ices. Where these ices are abundant, they can form thick layers or even entire planets, with a significant fraction of mass in frozen volatile metals. The ice giants of our solar system are named for this reality. Uranus and Neptune possess relatively small, rocky cores enveloped by thick mantles of water, ammonia, methane ices, above which lie atmospheres rich in hydrogen and helium. In addition to icy mantles, many moons and small bodies are dominated by water ice, sometimes mixed with silicates and organics, and warmed internally in some cases to produce subsurface oceans beneath an icy shell. The presence of ices in a planet's composition has major consequences for physical properties. Ices are less dense than rock, so ice-rich planets are puffier for a given mass, and they respond to heating and tidal stresses differently. In the case of bodies with internal heat sources such as tidal friction, ices can melt and produce oceans that may harbor chemical environments of astrobiological interest. Giant planets are dominated by the lightest elements. When the core of a growing planet achieves sufficient mass while embedded in a gas-rich disk, it can rapidly accrete the surrounding hydrogen and helium. The mass threshold for runaway gas accretion depends on temperature and opacity, but once passed, a planet can balloon into a gas giant with a mass many times that of the Earth. Jupiter and Saturn are classical gas giants. Their bulk composition is overwhelmingly hydrogen and helium, with trace enrichments of heavier elements that likely reflect the solids that seeded their formation. Yet even these giants are stratified. Deep within Jupiter, at pressures far exceeding those in terrestrial planet interiors, hydrogen becomes a metallic fluid, conducting electricity and contributing to the planet's powerful magnetic field. Above that layer sits a thick envelope of molecular hydrogen mixed with helium in modest amounts of heavier elements, capped with cloud layers where chemistry and temperature conspire to produce ammonia, water, and other condensates. The exact distribution of heavy elements between core and envelope is an active research question, and missions that measure gravitational fields and oscillations aim to infer the inner density distribution. Between the extremes of small rocky planets and bloated gas giants lies a population that has become central to exoplanet science: super-Earths and mini-Neptunes. These are planets with masses a few times that of Earth up to several times Neptune, exhibiting a bewildering range of radii and inferred compositions. Some appear to be scaled-up rocky planets with thick, high-pressure mantles. Others resemble small gas or ice giants with significant volatile envelopes. The distinction between a massive rocky world and a small gaseous one is not only a matter of mass and radius, but of formation history and atmospheric retention. The presence of a hydrogen-rich envelope dramatically lowers mean density and alters surface conditions. Understanding where the transition lies between super-Earths and mini-Neptunes touches on the physics of atmospheric escape, photoevaporation by stellar irradiation, and the efficiency of gas accretion in protoplanetary disks. A planet's atmosphere is its outermost compositional signature, and often the most visible. Atmospheres are constructed from the volatile inventory of the planet and its environment, and further sculpted by processes such as outgassing, photochemistry, impact delivery, and loss to space. Terrestrial atmospheres can be thin or thick, dominated by carbon dioxide as on Venus, nitrogen as on Earth, or nearly absent as on Mercury. The composition reflects both the degassing of the planet's interior and the interplay with surface processes. Earth's atmosphere bears the imprint of life in its high oxygen content, but without biological activity, the balance of gases would be very different. Giant planet atmospheres contain hydrogen and helium as primary constituents, punctuated by trace molecules that reveal deeper conditions. Spectroscopy has revealed methane, water vapor, ammonia, and a variety of disequilibrium species in giant planet atmospheres. And for exoplanets, transit and emission spectroscopy allow remote sensing of atmospheric chemistry. Clouds and hazes add complexity by obscuring deeper layers and introducing wavelength-dependent scattering. The presence or absence of particular molecules serves as a compass for models of planet formation and migration. Enrichment in heavy elements relative to the host star can indicate the accretion of solids, while the detection of exotic species may signal high temperatures or unusual chemistries. Magnetic fields are not made of material in the same sense as rocks and ices, but they are a manifestation of the internal composition and thermal state. A planet's magnetic field typically arises from a convecting, electrically conducting fluid in its interior. On Earth, the convecting metal of the outer core generates a geomagnetic field that shields the surface from charged particles. On gas giants, metallic hydrogen or convecting ionic ices can play a similar role. The presence of a magnetic field affects atmospheric retention by protecting against stellar wind stripping, and it can induce spectacular auroral phenomena. Conversely, the absence of a protective field can leave a planet's atmosphere vulnerable, as Mars demonstrates, where loss of significant atmospheric mass over geological time is tied to the loss of a global magnetic dynamo and to persistent interaction with the solar wind. Planetary differentiation is the process that separates a planet into layers of different composition and density. It begins when a growing planet acquires enough heat through accretional energy, radioactive decay of short-lived isotopes, and possible core formation energy to partially or fully melt. In a molten or partially molten state, denser materials sink toward the center, while lighter ones float. This segregation forms the metallic core beneath a silicate mantle and crust in terrestrial planets. Differentiation concentrates heat-producing radioactive elements in particular layers and establishes chemical reservoirs that can control long-term volcanic and tectonic activity. The timing and extent of differentiation depend on the initial composition and the heating history. Smaller bodies cool faster and may only partially differentiate, leading to a diverse set of interior architectures across planetary bodies. Heat sources within planets control their thermal and geological evolution. In addition to leftover heat from formation, planets are warmed internally by the decay of radioactive isotopes such as uranium, thorium, and potassium. Short-lived isotopes like aluminum can provide an early burst of heating that drives rapid differentiation in the first few million years. Tidal heating, caused by gravitational interactions with a nearby massive body or by orbital eccentricity, can be an intense local heat source, powering subsurface oceans and volcanic activity. Jupiter's moon Io is a dramatic example. Tidal flexing generates enough heat to drive intense volcanism, reshaping the surface on human timescales. The spatial and temporal distribution of internal heat influences whether a planet has plate tectonics, a stagnant lid, or episodic resurfacing, and it impacts the planet's capacity to sustain atmospheric outgassing in a long-lived climate. Materials beyond ordinary rock and ice sometimes appear in planetary makeups. Carbon-rich planets, sometimes dubbed diamond or carbide worlds in speculative literature, could form in disks with an unusually high carbon-to-oxygen ratio. In such an environment, silicon carbide and graphite become stable phases, and a planet's mantle could be dominated by carbides rather than silicates. While direct evidence for such exotic compositions remains tentative for now, the diversity of host star chemistries in the wide range of exoplanet densities allow for the possibility of unconventional interior chemistries. Metal-rich planets, perhaps the remnants of giant collisions, may have extreme iron cores and thin mantles. Water worlds with global oceans hundreds of kilometers deep would place water at high pressures where it formed dense, high-pressure ice phases, creating an interior structure unlike any familiar terrestrial planet. Understanding planetary composition relies on multiple observational strategies. For planets in our solar system, direct measurements come from spacecraft that orbit, fly by, or land on the world. Instruments can sample atmospheric gases, analyze surface rocks, probe magnetic fields, and measure gravitational fields to infer internal mass distributions. Laboratory experiments under high pressures and temperatures replicate interior conditions to determine physical and chemical behaviors of candidate materials. For exoplanets, remote sensing is the only recourse. The most fundamental quantity accessible for many exoplanets is the combination of mass and radius. Mass measured via radial velocity or transit timing variations, and radius measured from transit depths together yield mean density, a coarse but powerful constraint on bulk composition. A planet with a mean density similar to rock likely has a large silicate and metal-dominated interior, while a low density suggests substantial volatiles or a gaseous envelope. Spectroscopy of atmospheres during transits, eclipses, or direct imaging offers chemical fingerprints. Absorption lines of water, methane, carbon monoxide, sodium, potassium, and other molecules reveal atmospheric constituents and temperatures. Yet interpretation is often degenerate. Different combinations of interior structure and atmospheric thickness can produce similar bulk properties, and clouds or hazes can obscure spectral features. As observational precision increases, the statistical study of exoplanet populations begins to reveal trends. Planets cluster in radius and mass in ways that hint at common formation pathways in evolutionary processes. Planetary chemistry is a dynamic interplay of equilibrium thermodynamics and non-equilibrium processes. At high temperatures and pressures, certain minerals and compounds are stable, while at lower temperatures, volatile species condense. Chemical equilibrium predicts which molecules dominate a given environment if time allows. But many planetary atmospheres and surfaces are shaped by kinetic barriers, photochemistry driven by stellar ultraviolet radiation, and by inputs such as meteoritic material. For example, methane and water can coexist in a hot giant planet's atmosphere, but ultraviolet photons from the host star can drive complex photochemical pathways that produce hazes of complex organic molecules. On icy bodies, radiolysis by energetic particles can alter surface chemistry, producing radicals and complex organics from simpler ices. Surface weathering, whether by liquid water, wind-driven abrasion, or impact gardening, changes the exposed minerals and can mask deeper compositional signals. The solar system provides a convenient set of laboratories for studying these processes. Mercury, the smallest terrestrial world, has a dense iron-rich core and a thin silicate mantle with a tenuous transient exosphere composed of atoms sputtered from its surface. Venus, near twin in size to Earth, hides a hellish surface under a crushing carbon dioxide atmosphere and clouds of sulfuric acid. Its composition tells a tale of divergence where similar size and bulk composition produced radically different surface and atmospheric outcomes due to runaway greenhouse effects and different volcanic and atmospheric loss histories. Earth uniquely combines a metallic core, an active mantle with plate tectonics, a surface ocean that interacts with mantle-derived volatiles, and an atmosphere transformed by biological processes. Mars presents a smaller, colder terrestrial planet with a basaltic crust, signs of ancient water-altered minerals, and an atmosphere that has thinned over time. Out beyond lies the realm of the giants, Jupiter and Saturn, hydrogen-helium behemoths with possible dense cores and layered interiors, and Uranus and Neptune, whose higher proportions of ices give them distinctive densities and magnetic fields. Dwarf planets and moons, from Pluto to Europa, show that small bodies can be complex. Internal oceans, cryovolcanism, nitrogen-rich surfaces, and organic tholins suggest diverse chemical environments. Exoplanet discoveries have dramatically widened the palette of possible planetary compositions. Hot Jupiters orbiting extremely close to their stars show atmospheric chemistry modified by intense irradiation, with day-side temperatures high enough to dissociate molecules and produce ionized metals. Super-Earths found in tight orbits may be stripped rocky cores that once possessed thick envelopes. Observations of planets with larger radii, but relatively low masses point to volatile-rich mini-Neptunes, while discoveries of very dense, massive rocky planets challenge formation models. Direct imaging of young giant planets allows spectroscopic surveys of their atmospheres while still hot from formation, revealing molecular features and suggesting compositions shaped by cloudy, turbulent atmospheres. The diversity of exoplanets implies that while the same basic laws govern condensation, accretion, and chemistry, small changes in disk composition, stellar irradiation, and dynamical history can produce vastly different outcomes. The role of volatiles in planetary composition is central to questions of habitability. Water, carbon, nitrogen, and phosphorus are key ingredients for life as we know it, and their availability on a planet depends on its formation locale, delivery by planetesimals and comets, retention against atmospheric escape, and subsequent recycling through geological processes. A planet forming beyond the snow line can accrete abundant water ice, but if it migrates inward, that water may be maintained as an interior reservoir or lost from the surface, depending on temperature and pressure. Late-stage delivery of volatiles by comets and asteroids can enrich a planet, while large-scale impacts can both deliver and remove atmospheres. The balance between volatile delivery and loss is delicate, and small differences in early planetary dynamics can have outsized consequences for long-term habitability. Chemical fingerprints in planetary materials record the history of stellar nucleosynthesis and the local disk environment. Isotopic ratios, proportions of isotopes such as oxygen-16, oxygen-17, and oxygen-18, serve as tracers of the mixing and processing of materials in the early solar system. Meteorites preserve primitive material that predated planet formation and show a range of isotopic anomalies that hint at diverse stellar sources and at chemical fractionation in the protoplanetary disk. On planets, isotopic compositions can reveal atmospheric escape processes, water sources, and internal differentiation. For example, elevated ratios of deuterium to hydrogen in an atmosphere can indicate preferential loss of lighter hydrogen to space, enriching the remaining reservoirs in heavy isotopes. Such measurements are powerful tools for reconstructing the volatile and thermal histories of planets. Laboratory experiments and theoretical models underpin much of our understanding of planetary materials at extreme conditions. Diamond anvil cells and shock compression experiments permit the study of materials at pressures and temperatures that mimic planetary interiors, revealing phase transitions, melting curves, and equations of state that translate pressure into density for a given composition. These relationships enable the inversion of mass and radius data into plausible internal structures. Advances in mineral physics continue to refine our knowledge of how silicates, metals, and exotic ices behave at megabar pressures, affecting interpretations of giant planet cores and super-Earth mantles. Computational chemistry and thermodynamic modeling predict which minerals are stable under particular conditions, guiding expectations for planets formed under unusual elemental abundances. Cosmic chemistry also includes organic compounds, molecules built from carbon, hydrogen, nitrogen, oxygen, and other elements that appear in primitive bodies throughout the solar system and are synthesized in planetary atmospheres and surfaces under certain conditions. The synthesis of complex organics in irradiated ices, in hydrothermal vents where hot, mineral-rich fluids mix with colder reservoirs, and in the atmospheres of gas giants via photochemistry contributes to a rich inventory of prebiotic molecules. The presence of complex organics does not imply life, but it does provide the raw material from which life could, under certain circumstances, emerge. Ultimately, a planet is a dynamic chemical factory. Its composition reflects a sequence of processes: the primordial mix of the interstellar cloud, the condensation behavior in the protoplanetary disk, collisions and accretion, internal differentiation and thermal evolution, atmospheric chemistry and escape, and surface interactions that recycle and alter materials. Two planets formed in the same system can diverge dramatically if one is struck by a giant impact that strips its mantle, or if one happens to retain a thick atmosphere that insulates and drives geochemical cycles. The observable clues we use to read a planet's composition, density, spectra, magnetic field, geological features, are fragments of that longer tail, and interpreting them requires an interplay of observational data, laboratory work, and physical intuition. In the coming decades, a combination of new telescopes, more sophisticated space missions, and refined laboratory techniques promises to deepen our understanding of planetary composition. Spacecraft that probe beneath surfaces with radar and interactively sample atmospheres and dust will continue to refine models for planets close to home. For distant worlds, next-generation observatories with high-precision spectrographs and coronagraphs will open windows into the atmospheres of smaller, cooler planets, searching for signatures of water, oxygen, carbon dioxide, and other potential biomarkers. The growing statistical sample of exoplanets will clarify how common various planetary types are and whether our own blend of rock, water, and life-friendly conditions is rare or typical. Thinking of planets as made of rock, ice, and gas is a useful starting point, but the truth is richer and more surprising. Planets are assemblages whose components have been sorted and reshaped by gravity, chemistry, and time. They may be dominated by metals forged in ancient stars, by water frozen into deep mantles, by hydrogen heated to metallic states, or by exotic compounds little represented on Earth. They may carry atmospheres that have been altered by life, or atmospheres that have been swept away by stellar winds. Each planet is a chemical archive, and each observation is a page revealing how matter organizes itself under different conditions. As our techniques improve and our discoveries expand, the catalog of planetary materials will grow, and with it our appreciation of how versatile and creative the cosmos can be in making worlds. To stand in front of a planet is to read a composite story of origin and change. The iron heart that once sunk through molten rock, the silicate shell that later cracked to allow volcanic breath, the frozen molecules that fell from a colder region of the disk, the gases stripped or accreted by a nearby star. All these elements converge to produce the physical object we call a planet. Material composition informs everything from a planet's surface weather to its magnetic shield, from the likelihood of oceans to the potential for harboring life. Understanding what planets are made of therefore connects the mechanics of astrophysics with the chemistry of materials, the dynamics of atmospheres, and the slow sculpting of geology. It is a field that spans disciplines, that uses both telescopes that gaze across light years and instruments that crush rocks between diamonds to recreate the pressures at planetary cores. When we look up and see the point of light that is a planet, especially one orbiting a distant star, we should remember that its visible properties are a thin skin on a deeper interior shaped by a complex recipe. Some planets will surprise us with compositions that defy Earth-centric intuition. Some will be familiar in their chemistry, showing water, rocks, and an atmosphere that cycles between liquid and gas. Others will challenge our models, appearing as dense iron worlds or as airy, puffy mini-Neptunes. The diversity of planetary materials is a central reason why the study of planets is so compelling. Every world is a laboratory of physics and chemistry, a unique experiment in what matter does under the influence of gravity and energy. A final thought returns to the human urge to classify and understand. Labeling planets as rocky, icy, or gaseous is a useful shorthand, but it must not blind us to the continuum in between, to the gradations and hybrids that populate the universe. The same basic elements, hydrogen, helium, oxygen, carbon, nitrogen, silicon, and iron, combine in myriad proportions and states, their behavior conditioned by temperature, pressure, and history. In that combinatorial richness lies the source of planetary wonder. To ask what planets are made of is to ask how the universe takes simple ingredients and, through chemistry and physics, sculpts complexity, diversity, and occasionally the conditions that enable conscious beings to wonder about it all. Under the surfaces of planets, matter is never truly still. Even when a crust appears solid and unchanging, atoms vibrate, minerals slowly transform, and heat quietly diffuses outward. Geological time stretches events across millions to billions of years, turning molten beginnings into layered spheres that cool unevenly. This slow cooling leaves fingerprints in a planet's composition. A thick lithosphere may lock elements into rigid plates, while a hotter mantle may remain convective, circulating minerals and gases that eventually escape into the atmosphere. These processes mean that what planets are made of is not fixed at birth, it evolves. The chemistry of a planet today can differ significantly from its primordial state because materials have migrated, melted, crystallized, been vented to the surface or swept away to space. On Earth, plate tectonics constantly cycles material between mantle and crust. Silicates melt in volcanic regions and rise as magma, building continents and seafloors. Weathering breaks rocks into sediments that are buried, heated, and sometimes metamorphosed into new rock types. Gases released through volcanic activity replenish the atmosphere with carbon dioxide, sulfur dioxide, and water vapor. This recycling makes Earth's surface composition dynamic, helping regulate climate and maintain a balance of volatiles suitable for life. In contrast, planets without sustained tectonics or volcanism gradually seal their internal chemistry away. Mercury and the Moon each bear ancient crusts largely unchanged for billions of years. They are time capsules of early planetary differentiation, retaining the minerals and textures forged during their first geologic chapters with little later modification. Water plays a special role in altering planetary materials. When liquid water is present at or near the surface, it acts as a solvent and a transporter of ions. It dissolves minerals, carries dissolved elements into pores and fractures, and helps precipitate new mineral forms. On Earth, water is responsible for vast geological cycles. Limestone caves carved from carbonate dissolution, clay produced from silicate weathering, hydrothermal vents that create sulfide-rich deposits at mid-ocean ridges. Water also alters the mechanical properties of rocks. Hydrated minerals can become weaker and more pliable, enabling plate tectonics. Mars preserves ancient river valleys carved when water was briefly abundant, and minerals such as clays and sulfates reveal that its surface once experienced chemical weathering in water-rich environments. The icy moons of Jupiter and Saturn contain water in forms Earth never sees naturally. Beneath their frozen crusts lie high-pressure ice polymorphs that form only under enormous pressure, introducing alien mineralogy into planetary composition. Pressure is a master sculptor of planetary materials. Deep inside planets, pressure rises to thousands or millions of times atmospheric pressure. Under these conditions, atoms are forced into tighter arrangements, and familiar materials transform into exotic phases. In Earth's lower mantle, silicate minerals change from one crystalline structure to another, becoming denser and altering how heat is transferred. The boundary between mantle and core is an environment where iron, silicon, oxygen, and sulfur may mix in unusual ways, forming alloys difficult to reproduce in laboratories. Even deeper, the solid inner core crystallizes from a liquid outer core, a process that releases latent heat and light elements, feeding the convection that powers the magnetic dynamo. In giant planets, pressure can be so high that hydrogen, a gas in ordinary conditions, becomes a metallic liquid. This material is thought to exist in Jupiter and Saturn, possibly forming a thick shell around any solid core. Metallic hydrogen is responsible for their immense magnetic fields and may influence heat transport and planetary rotation. Temperature adds another layer of complexity. Near a star, intense heat strips surfaces of volatile ions, drives atmospheric escape, and fosters chemical reactions that would not happen in colder environments. On hot exoplanets, minerals can vaporize into the atmosphere, creating clouds not of water but of silicates or metal oxides. Astronomers have identified worlds with temperatures high enough to melt rock on the day side, allowing material to evaporate and condense, and it suggested rock rain on the night side. At the other extreme, cold worlds far from stars preserve primordial ices and organics in pristine condition. At temperatures near absolute zero, molecules lock into structures that can endure for billions of years without alteration. Comets and Kuiper Belt objects are archives of the early solar system, their composition revealing what existed before planets differentiated and evolved. Rotation and magnetic fields further influence planetary chemistry. Rapid rotation can stir a planet's liquid outer core, sustaining a magnetic field that shields the atmosphere from erosion. Without such protection, solar wind particles can strip lightweight molecules, leaving behind heavier constituents. Mars once possessed a thicker atmosphere and possibly flowing water. But as its internal dynamo shut down, the lack of a magnetic shield accelerated atmospheric loss. The remaining air is now thin and dominated by carbon dioxide, with traces of noble gases that have become enriched as lighter gases escaped. This atmospheric evolution leaves behind a composition drastically different from the one early Mars likely had. Similarly, Titan, Saturn's largest moon, retains a dense nitrogen atmosphere thanks to its distance from the sun and low temperatures, conditions that make volatile retention much easier. Chemistry takes advantage of that protected envelope. Ultraviolet radiation splits molecules high in Titan's atmosphere, generating a cascade of reactions that form complex organic aerosols, coating the moon in an orange haze. Planets are not isolated systems. Impacts from asteroids and comets deliver new material and sometimes modify planetary composition dramatically. During their youth, planets experience intense bombardment that contributed to their volatile inventories, including Earth's water and organics. Large impacts can melt crust, mix layers, or even remove massive amounts of material. The leading hypothesis for the moon's formation suggests Earth was struck by a Mars-sized body, vaporizing and mixing portions of both worlds. The composition of lunar rocks reflects this blended origin, similar in many ways to Earth's mantle, but with key differences that provide clues to the giant impact's dynamics. Later impacts continue to alter surfaces, excavating materials from depth and spreading them across plains. On icy bodies, impacts can expose fresh ice or ammonia-rich regions, revealing interior chemistry otherwise hidden beneath dark radiation-processed crusts. Stellar influences extend beyond heat and radiation. The elemental composition of the star itself shapes the composition of its planets. Stars with higher metallicity, meaning a greater abundance of elements heavier than hydrogen and helium, tend to host more planets, and those planets can have richer inventories of rock-forming elements. Variations in stellar carbon to oxygen ratios may give rise to entire families of planets with unusual chemistries. In regions where carbon dominates, planet-building material may favor carbides over silicates, potentially forming planets with graphite-rich crusts or diamond interiors. Likewise, stars enriched in volatile elements could produce water worlds with thick ice mantles in deep subsurface oceans. The periodic table is the basic alphabet of planetary construction, but the proportions available in the protoplanetary disk determine which words nature can spell. As planetary astronomy advances, scientists now explore composition not as a single label, rocky, icy, gaseous, but as a continuum influenced by dozens of variables. A planet's density alone can hide a multitude of structural possibilities. Two planets with the same mass and radius might differ internally. One could have a large iron core and thin mantle, while the other could have modest core size but vast amounts of high-pressure ice. Without direct seismic or in-situ measurements, distinguishing such possibilities is challenging. That is why multiple lines of evidence matter. Gravity data reveals how mass is distributed inside. Spectra reveal surface or atmospheric chemistry. Temperature profiles provide clues to outgassing and volcanism. Magnetic field strength may suggest the presence of a convecting metallic region. Future exploration seeks to peel back more layers of these chemical mysteries. Missions like Europa Clipper and Dragonfly will study ocean worlds that mix rock and ice in fascinating ways, possibly revealing environments where water interacts with mineral-rich seafloors to produce complex chemistry. Samples returned from Mars may tell us how its atmosphere and crust evolved as the planet cooled and dried. Telescopes being built now will examine the atmospheres of Earth-sized exoplanets, searching for gases that betray geological processes, or even biological ones. The detection of oxygen, methane, or certain combinations of gases could reveal that chemistry on some planets is driven by more than physics alone. In our quest to understand what planets are made of, we repeatedly discover that matter under planetary conditions behaves in ways unfamiliar to us. Solid rock can flow like very slow liquid. Ice can be harder and denser than granite. Gas can become metallic. Silicates can form exotic crystals at depth. Carbon can assemble into kilometer-thick layers of diamond under crushing pressure. What seems simple on the surface unfolds into complexity the deeper we look. The story of planetary composition is ultimately a story of transformation. A planet begins as dust and one, simple building blocks drifting in a nebula. Gravity brings those particles together, heat melts them, chemistry reorganizes them, and time sculpts them into layered worlds. Some remain close to their original state, small, frozen relics orbiting the sun unchanged. Others evolve dramatically, inventing oceans, continents, atmospheres, and climates from the same starter ingredients. And a very few, at least one that we know of, turn their chemical makeup into something profoundly new: life. Everything that makes Earth habitable, from the iron that fuels its magnetic shield to the water that shapes its geology to the oxygen we breathe, comes from the same cosmic ingredients found everywhere. What differs is proportion, arrangement, and evolution. By studying the compositions of other planets, we learn which combinations of matter lead to barren rocks and which lead to living worlds. So when we ask what planets are made of, we are not only identifying their materials, We are asking how those materials came together, how they changed, how they influence the present and future of each world. We are asking how chemistry becomes geography, how physics becomes climate, how matter becomes meaning. In every planet, from the scorched lava planets hugging their stars to the cold ice giants drifting in distant darkness, there is a recipe, a process that tells how atoms find their places within a planet's vast interior. The more planets we discover, the clearer it becomes that nature is wonderfully inventive. Worlds can be sculpted from iron, from silicates, from ammonia and methane, from hydrogen and helium, from combinations we have not yet imagined. Some carry oceans under ice. Some may have volcanoes of frozen nitrogen. Some may be covered in hydrocarbon lakes. Some may be wrapped in atmospheres so thick that sunlight never reaches the ground. Each of these forms arises from matter responding to gravity and heat, obeying universal laws yet producing unending diversity. Our understanding is still incomplete. There are planets too distant to resolve, materials too extreme to fully simulate, mysteries hidden beneath kilometers of cloud or crust. But with every new mission, every instrument, every experiment in a laboratory that squeezes minerals to the pressures of planetary cores, we get closer to reading the full story encoded within planetary matter. To stand on a world, whether real beneath our feet or imagined through data, is to meet the outcome of cosmic chemistry. The soil, the air, the mountains, the oceans, the magnetic fields, the clouds, the heat within, all are expressions of what that planet is made of. Composition determines character. It sets the stage for a planet's weather, climate, tectonics, habitability, and destiny. Worlds are made of atoms, forged in stars, shaped by disks, sculpted by heat and gravity, transformed by time. They are chemical sculptures on cosmic scales, each unique, each telling its own story. Our task as explorers is to listen, to decode those stories from the hints planets offer us, and to appreciate how a handful of elements can assemble into countless varieties of planets. Some familiar, some alien, all extraordinary. When we zoom out and consider planets as a class of objects, a beautiful pattern emerges. They are built from the same cosmic ingredients, yet assembled through different recipes, cooked in different cosmic ovens, seasoned by different histories of impacts, migrations, heating, cooling, and chemical transformation. The diversity we see across our solar system and beyond is not chaotic. It is the logical outcome of physics and chemistry playing out at grand scales over billions of years. Planets are ultimately a story about matter organizing itself into structure, complexity, and sometimes the potential for life. The most fascinating aspect of planets is that their composition is not a static secret hidden deep within. It is dynamic. A planet's materials react to changing environments. Heat can melt rock into magma or vaporize atmospheres into space. Pressure can turn ice into exotic crystals or transform common minerals into weird, ultra-dense forms. Solar irradiation can break molecules apart and rebuild them into entirely new compounds. The materials inside planets are constantly evolving, sometimes slowly over geological ages, sometimes abruptly through violent events like volcanic eruptions or asteroid collisions. A planet is never truly finished. It is always becoming. Even a planet that appears quiet on the outside tells a chemical story inside. Uranus, for example, looks calm and bland, but beneath its pale atmosphere, ammonia and water are likely crushed into hot, high-pressure superionic states where hydrogen ions roam freely like sparks inside a storm. That inner environment is so bizarre that we barely have words to describe it. Deep inside Saturn, helium rains downward like shimmering metallic droplets. In Jupiter's mantle, hydrogen becomes so compressed that electrons detach from their atoms, turning an ordinary gas into a gleaming, electrically conductive metal. Inside Earth, iron crystals slowly grow and align, helping sustain the magnetic field that shields life from the harsh solar wind. Composition is not just a list of ingredients, it is a living cycle of transformation. When astronomers study exoplanets, composition becomes a history book. The amount of methane or carbon dioxide in an atmosphere reveals whether the planet formed in a cold or hot region, whether it migrated from far away, whether its interior is venting gas or sealing it tightly inside. Heavy elements tell us whether giant planets grew slowly over millions of years or suddenly captured gas in a burst of runaway growth. Crustal materials, if someday detected on distant worlds, could reveal the presence of tectonics, erosion, or even biological activity. Chemistry is a detective, uncovering events that shaped worlds long ago. And composition doesn't just tell us where a planet has been, it tells us about its future. A rocky planet with too little water and carbon might remain barren forever, never developing oceans or weather cycles needed to nurture ecosystems. A planet with too much volatile gas, like Venus, might become a greenhouse inferno. A gas giant with a heavy element-rich core might slowly lose its atmosphere, eventually leaving behind only a dense remnant. A planet is defined not only by what it is made of, but also by what it might become. When we examine composition across the full spectrum of planets known today, some profound questions emerge. Is Earth's combination of rock, metal, water, and air unique, or is it common? Did the ingredients that make life possible only come together once? Or do countless other planets share similar recipes? Are we living on a cosmic miracle or simply one example among an uncountable population of habitable worlds? The more planets we find, the clearer it becomes that nature loves experimentation. There are planets where iron dominates so heavily that the world may shine like polished metal from core to crust. There are planets made almost entirely of carbon, where diamond mountains might rise under alien skies. There are planets drowning in deep oceans, thousands of kilometers thick, with exotic ices forming solid walls beneath unimaginable depths. There are planets where mineral clouds rain gemstones, where silicate dust storms rage, where molten rock replaces water as the main surface liquid. And these might just be the beginning. Take the concept of a carbon planet. In such worlds, carbon replaces oxygen as the most influential building block, and materials like graphite and diamond substitute for basalt and granite. Instead of silicate volcanoes erupting lava, these worlds might erupt carbon-rich fluids or methane geysers. Organic chemistry could flourish in unexpected ways, producing molecules never seen previously in planetary environments. They might be dark, glimmering planets reflecting almost no light, hiding their secrets in obsidian shadows. If life ever rose there, it would evolve under conditions utterly unlike our own, yet still shaped by the same chemical principles. Or imagine a planet where high temperatures keep rock molten across the entire surface. Instead of continents and oceans, glowing lakes of lava would churn and ripple. Silicate vapor could form thick atmospheres that shimmer like heat waves. Mineral clouds would form and rain droplets of liquid rock back to the surface. Such a world seems hostile, but early Earth itself experienced periods like this during its fiery youth. Planetary composition includes the story of time. Every planet transforms, cools, and matures, often passing through wildly different physical phases. Now swing the pendulum in the other direction. A rogue planet drifting through the starless darkness, freezing endlessly. Its atmosphere collapses into frost. Its oceans turn to buried ice. Yet geothermal heat from radioactive elements might melt water deep below, forming secret subsurface seas. The chemistry of life could continue in hiding, powered by internal energy rather than sunlight. A planet made of cold stone and ice could still hold warmth and possibility in its heart. Even moons remind us that composition matters as much as scale. Europa's vast water ocean exists because its composition allows ice to flow and crack and melt under tidal forces. Titan's thick nitrogen atmosphere and liquid methane lakes form because of temperatures low enough for hydrocarbons to behave like water. The ingredients do not merely exist. They respond to conditions in ways that shape landscapes, climates, and opportunities for life. Change the composition just slightly, and the entire character of a world changes with it. This is why scientists search not just for Earth-like planets, but for Earth-like compositions. We are looking for planets where rock and metal are abundant enough to create continents and magnetic fields. We look for worlds with carbon dioxide and water vapor, the chemical foundations of stable climates. We look for places where temperatures allow molecules to react, where elements necessary for life are not locked permanently in inaccessible minerals, or lost to space. We seek the familiar because it gives us hope, but we are also learning to appreciate the unfamiliar because every exotic planet expands our understanding of what a world can be. Future missions will bring composition studies into a new era. Space telescopes will analyze starlight passing through alien atmospheres, breaking it into colorful spectra that reveal the fingerprints of molecules. Seismology on Mars and maybe one day on icy moons will show the shapes and thicknesses of buried layers. Landers may someday drill beneath the surfaces of Europa, Enceladus, or Titan, sampling materials that have never touched sunlight. Humans might walk on Mars and chip rocks that formed before Earth existed. Each measurement, each fragment of mineral or bubble of gas will unlock another piece of the deep chemical puzzle. At the deepest level, planetary composition connects us to the birth of the universe itself. The hydrogen in gas giants was forged in the Big Bang. The oxygen in Earth's rocks was created in ancient stars. The iron in your blood once glowed in the core of a supernova. The carbon in every living cell on our planet was produced in the hearts of dying suns and scattered into space as cosmic dust. Earth is not just made of rock and water, it is made of memory, matter that has traveled across cosmic time to gather here in this moment. So when we ask, what are planets made of? We are really asking a much bigger question. We are asking where we come from. We are asking why there is structure instead of chaos, worlds instead of dust. We are asking how lifeless atoms can build mountains, oceans, atmospheres, storms, and, eventually, creatures capable of wondering about their own composition. Planets are chapters in a universal story, the story of how simple elements combine to form complex worlds, and how those worlds evolve into places that can think, feel, and dream. Every planet, from the most barren to the most welcoming, is a laboratory where matter tries out new forms. Some worlds end in silence. Others may someday echo with voices. Composition is the blueprint of possibility. It decides whether a world becomes a furnace or a cradle, a diamond orb or a blue marble, a dead rock or a home. Our understanding is still young. With each new discovery, we rewrite the definitions of what planets can be made of. But we already know one truth with certainty. Planets are not random lumps of material. They are the universe expressing creativity through chemistry and physics. They are sculptures carved from stardust. They are experiments, ongoing and evolving. And we are living proof that one of those experiments worked. The more we search, the more worlds we will find. The more worlds we find, the more we will learn about the ingredients that build them. And somewhere out there, orbiting some distant sun, there may be a planet that shares not only Earth's composition, but also its gift of life. A place where oceans glimmer under alien constellations, where continents shift slowly over time, where air carries scents of unfamiliar forests, and where beings look up at their sky and wonder, just as we do, what their world is made of. Perhaps someday we will meet those worlds. Perhaps someday we will trade stories of our composition, rock and water, carbon and oxygen, memories of ancient stars, and realize that in a universe so vast, distant planets are not strange at all. They are kin, built from the same cosmic ingredients, guided by the same forces, forever orbiting in the grand shared story of existence.